Something else that we use often is the MUX. Exclusive OR can be built using transistors, which I'm not going to show. Also, it can be built using AND gates and OR gates and inverters, also NAND gates. And same thing with the gate I'm showing now, which is a MUX or a multiplexer. A multiplexer is this. It says if S is 0, see the 0 up there. If S is 0, A passes through. If S is 1, B passes through. Okay? Another way of writing it would be W becomes, if S is 1, then B, otherwise A. Okay? Again, W is, if S is 1, then B, otherwise A. And this table shows that if S is 0, W becomes A. If S is 1, W becomes B. Okay, so this is the red line here, and this one is the yellow line here. And if you want to write the complete truth table for it, if S is 0, okay, if S is 1, which is this part, and you are seeing that your W is the same as your B, but then if S is 0, your W is the same as your A. Okay? Again, inside this, you have AND gates, OR gates, inverters. You can also build this using transistors, meaning that you can have a series of transistors. I'm not going to go through that for the NMOS transistor. And I can do that, but I guess it's gonna it's not a difficult thing to do, but if let's only draw it this way. There is an N block, there is a P block, okay, and then there is this W, and the N block and the P block have the A input, have the B input. Okay, this is without having to go through the transistor structure of it. Okay, the upper part is PMOS transistor, the lower part is NMOS transistors put in series and parallel transistors, and then eventually it builds the W output. In cases you also need inverters for some of the inputs, but this is generally the way we represent CMOS structures. And the same thing with XOR. You can also do a PMOS on top and NMOS at the bottom, and again, in cases you may need the complement of the inputs as well. All right. Why do we include this as regular gates? Because when we are doing a logic function, it becomes very convenient to have a structure like that passes either one of the inputs to the output. Plus, that multiplexer is a complete structure, meaning that any function can be realized using multiplexers. Multiplexers can be cascaded, meaning that if you have a 2-to-1 multiplexer, this is a 2-to-1 multiplexer, 2-to-1 multiplexer, okay, or 2-to-1 multiplexer, meaning that it has two inputs, it has one output, and you are selecting one of the two inputs. And you can make that into a 4-to-1 multiplexer, meaning that you have four inputs, A, B, C, D, and then you have two select lines, S1 and S0, and you will be selecting either one of the inputs. You can build an 8-to-1 multiplexer, and you can just cascade them into larger structures. And So it is a complete function. It is very convenient for describing, for representing logic functions. Let's say, for example, you have an 8-to-1 multiplexer, meaning that you have 3 select lines, you have 1 input line, and you have 8 input lines, and you can build a 4-variable function, a function with 4 variables very easily using an 8-to-1 multiplexer. This is a 4-to-1 multiplexer, and we call it the multiplexer gate or multiplexer structure. And again, you can use, let's just, because we have talked about this, this is a 2-to-1, this is a 2-to-1, A, B, C, D. This is another 2-to-1. I put a 0 here, meaning that that input is selected when its select input is 0. Okay. Now, if my, I'm going to connect S1 to this and S0 here. Now look at that. If S1 is 0, that means the upper part is going to be selected. And then if S0 is also selected, A is going to go through. Okay? So, a 0 here, a 0 here, a 0 here, a 0 here. Let's A go through. Let's A go through. Okay? And for S1, S0, 0, 1, 0, 1. Okay? Let's see. 0, 1. Still, the upper part is going to go through, but then because S0 is 1, B is going to go through. Okay, B is going to go through. For S1, S0, 1, 0, 1, 0, the lower part is going to go through. So I have a 1 here. I'm sorry, a 1 here, a 0 here. Because S1 is 1, the lower part is going to go through. Because S0 is 0, the upper part of the lower part is going to go through. And therefore, this is what's going to happen. And finally, if I have a, let's use a color we have not used. If I have a 1, no, same as the background, orange, I guess. If I have a 1, 1, then, okay, a 1, 1, D is going to go through. A 1, 1, the lower part of the this multiplexer is going to go through, the lower part of this is going to go through, and therefore D is going to appear on the output. Okay, you can do the same thing for 8-to-1 multiplexers as well. The good thing or the beauty of multiplexers is that you can turn it into any gate. Look here, I'm connecting A to S, and if I'm taking this original table from the multiplexer, and I'm connecting A to S, and what it means is A and S are going to be the same, and therefore anything that A and S are different is going to be eliminated. And once that happens, now look at what remains, which is this part and this part. Okay, in this case, only look at A and B. A, B, 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. What it means is this multiplexer turns into an AND gate. Connect B to S, and it means that from the original truth table, all those cases that B and S are different is going to be eliminated. So SMB01 is gone, 01 is gone, 10 is gone. All the cases that are different is going to be eliminated. Now let's look at what remains. AMB00 is a 0, 10 is a 1, 01 is a 1, 11 is a 1. What we have is an OR structure, okay, an OR function. I can turn it into an XOR, I can turn it into an inverter, and what it means is I can use a multiplexer in place of everything else. That's why in programmable devices and in FPGAs, field programmable logic devices, or for field programmable gate arrays, FPGAs are. In FPGAs, they use a lot of multiplexers for realizing a lot of functions. And this is just the structure I was showing, and cascading the multiplexer. The word cascading is a good thing, meaning that you put the lower level structures into turning them into upper level structure. That's not only for multiplexers. Let's look at a 2-input AND gate. If you want to have a 3-input AND gate, this is how you do it. If you want to have a 4-input AND gate, this is how you do it. If you want to do a 5-input AND gate, you can just put AND gates. You can easily cascade them. But then if you do if you want to do a 4-input, it's better to do it this way, because this way you have a long path from some of the inputs to the output, whereas in this case, the worst case, or the path, the delay path from the inputs to the output is more balanced. XOR is the same way. This is a 2-input XOR, this is a 2-input XOR, and this is a 4-input XOR. This is a 5-input XOR. Okay. And so you can just build those. But for the NAND and NOR, you cannot do it that easily. If this is a NAND, you want to do a 3-input NAND. What you got to do is you have to turn this into an AND first, and then NAND these together. Okay, so this is A, B, C, all NANDed. All right, that is a multiplexer, and this is the concept of cascading. And cascading OR gates into upper structures is also very easily possible. So far, the gates we have shown are gates that the output is either a 0 or a 1. Okay, meaning that the gate has a pull-up structure, P-type, a pull-down structure, N-type. I guess I need some other. Well, let's go to the next slide. Yeah. So far, all the gates have a P structure, an N structure, and either the output is driven through the pull-up structure or through the pull-down structure, putting a 0 or a 1. There are other gates that do not necessarily have the driven output at all times, and that is a tri-state gate. A tri-state gate is like what I'm showing here. It has a control input, C input, and it has an A input, W output. The way it works is the following. If C is 1, then A passes through. If C is 0, then nothing passes through. Nothing in logic means logic value Z. Okay, so we have 0, 1, Z, and X. Nothing means logic value Z. But logically, what I'm showing here is absolutely no different from this structure here. What I said is, logically, a single NMOS transistor can work as a what we call a tri-state buffer, a three-state buffer, or we call it a we call this a pass transistor. Okay, so a pass transistor can work in place of a tri-state structure. I was very careful in saying that this is logically the same as this over here. Electrically, these are different. This one, when C is 1, the output is driving current from the A input. Okay, I'm talking about the NMOS transistor. Let's Control L. Okay, yeah. This NMOS transistor, if it is 1, the output is driving current from the input A, but then if this is a three-stage structure, if C is 1, W is still driving current from the pull-up and the or from the supply or from the ground, and therefore electrically these two structures are different. Logically, there is no difference. Let's read this. It says W becomes if C is 1, or if C, then A, otherwise capital Z, that means high impedance or open or not driven at all. And this truth table shows that if this is 0, this becomes a Z. If this is 1, W becomes an A. Let's look at this structure below and let's see what happens here. Okay, what happens is if S is 0, okay, if S is 0, this lower transistor will be not conducting. The upper transistor, because there is a 1 here, will be conducting, and therefore A is going to go through to the output. On the other hand, if S is 1, okay, if S is 1, because the inverter output becomes a 0, this upper transistor will not be conducting, but because S is 1, the lower transistor will be, the lower gate, the lower tri-state gate will be conducting, and therefore the output becomes what is on B. And therefore, what is this? This is a multiplexer. This function is absolutely no different than a multiplexer. You can build a multiplexer also by having a PMOS and an NMOS. Okay, this is your A, this is your B, this is your S input. If S is 0, A will be going through. If S is 1, B will be going through. The same thing as what we have here, again, logically. The problem with this multiplexer is that when it is conducting either from the upper path or the lower path, it is driving current from my A and B inputs, whereas this structure, because these tri-state structures have their own supply and ground, they will not be putting burden on my inputs. All right, these are more logic structures, and tri-state gates are important. Tri-state gates are good for busing, where you have various sources putting data on a bus. Actually, multiplexers and these tri-state structures are so close that sometimes instead of multiplexers, we use tri-state gates implementing multiplexers, and sometimes we call a multiplexed bus, sometimes we call a tri-state bus, which functionally they are very similar. Earlier we talked about FPGAs, or field programmable gate arrays. Field programmable gate arrays have non-dedicated logic functions that you can program them to make them do anything you want. And therefore a multiplexer is good because you can turn a multiplexer into whatever you like. Another function that you can turn, or another structure that you can turn to whatever you want, is a what is called a lookup table. Okay, a lookup table is a truth table. is a truth table, let's say with 3 inputs or with 4 inputs. And when you are programming a programmable device or an FPGA, you will be programming the values into various positions of this table. Look at lookup table as a 1-bit memory. Okay, so you have 3 address lines. Address 000 points to location 0. Address 001 points to location 1. Location 2, address 111, that means ABC 111, points to location, I'm writing, okay, these are the addresses, these are the decimal values for the addresses, and in these addresses there are these values stored. Okay, what it means is I can turn this lookup table into whatever 3 variable function I want. Okay, and since FPGAs use that very often, therefore we in a way look at it as a logic structure or a programmable logic structure. This particular lookup table, W becomes 1 if ABC is W is 1 when ABC is 0, 1, 1, 1, 0, 1, 1, 1, 0, or 1, 1, 1. Okay, what logic exactly I'm following here? Let me think about it a little. Okay. All right. The output becomes 1 when 2 or more of the inputs is 1. Okay? When 2 or more of the inputs are 1. If A is 1, B is also 1, I'm sure the output is going to be 1. When A is 1, C is 1, I'm sure the output is going to be 1. Or when A, B, and C are all three of them are 1, then the output is going to be 1 too. Okay, what it means is I have programmed this lookup table to function as such. Okay? Actually, let's program a lookup table to function as an XOR logic. Let's program a lookup table to function as an XOR. W becomes XOR of A, B, C. Okay, what did I say about XOR? I said that okay, about XOR, I said that the output becomes 1 when the number of ones on the inputs is odd. Okay, 0, 0, 0, the output is 0. Odd. 0, 1, 2 is 0, 1, 0, odd. 3 is even. 0, 1, 1, 2 ones is even. 4, 1, 0, 0, 1, 1 is odd. 5, 2 ones is 0. 6, 2 ones is 0. 7, 1, 1, 1, odd. And therefore this is a 1. Okay, so I have programmed my lookup table to function as an XOR. Program a lookup table to function as a 3-input multiplexer or a 2-to-1 multiplexer, and so it becomes a component that you can use it for anything you want, or program it to function as a 3-input AND gate or NAND gate. All right, we have covered basic logic structures, and these logic structures are useful in doing circuits, logic circuits, and so this for now is Yeah, I guess I'm also, before ending, I am also showing the majority function, which is, again, not exactly a single gate, a simple gate, but then it's a little bit more function to it. Since I've already talked about an XOR, a MUX, a lookup table, let's also talk about another function which we call it a majority function or a majority gate. A majority function, the output becomes a 1 when majority of inputs are 1. Okay? Actually, if you go back and listen to what I said about this gate, I said if 2 or more of the inputs are 1. That means I have programmed this lookup table to function as a majority gate. Okay? And a majority gate is also a gate that in a lot of cases I can assume that I have the inputs, I have the gate level structure of it. I can build a majority gate using a pull-up structure, a pull-down structure with some inverters maybe. And in the list of our primitives, it's a good thing to have the majority function. All right, let's write this majority function. See, 001, let me use a different color. 001, the majority obviously is not 1, and therefore the output is 0. 001, the majority is not 1, output is 0. 010, the majority, well, there are 3 inputs, and then 2 of them are 1, and therefore the majority are 1, and then the output is 1. The majority are 1, the majority, and therefore the output becomes 1. And we can write this as Maj, A, B, and C. And another format I'm showing here, which we will use later on, is to write this as sum of the min terms. Look, the output is 1 when the input decimal value is 3, or 5, or 6, or 7. We say that these are the min terms of the function, or the places that the output is 1 is called, in terms of all the inputs, is called a min term. And any function can be represented as sum of the min terms 3, 5, 6, and 7. Okay, so if there is not a simple Boolean structure that we can, or Boolean expression that we can write to represent a function, one alternative would be to just write all the min terms. Actually, any function you have seen so far, I can represent it as sum of the min terms. Let's do the XOR. So we can say that XOR A, XOR B, XOR C is the same as A, XOR B, XOR C is the same as A, XOR B, XOR C, and that is the same as, now look at the min terms. XOR of the 3 inputs is, we can also go back and look at the previous one, but if the number of zeros, the number of ones is odd, that means 1, 2, 4, 7. Okay, which are the numbers actually 1, 2, 4, 7 in this case. Okay, and therefore XOR can be represented as such as well. All right, we are done with our logic structures and a little bit beyond logic structures, more complex structures also. Now that I mentioned complex, a CMOS NAND gate is a NAND gate, a CMOS NOR gate is a NOR gate. If you go beyond just NAND gate and NOR gate, you go into majority gate using CMOS logic with pull-up PMOS pull-up and NMOS pull-down structures, that is called a complex gate. Okay, therefore a multiplexer, an XOR, a majority function, all of these can be implemented using a complex gate structure. Another complex gate structure which you may hear sometime is, let me use black here, is AOI and or invert. That means the output is a 4-input and or invert is A ANDed with B, C ANDed with D, and then the whole thing complemented. This is AOI, and or invert. Okay, and the logic notation for it is this: A, B, C, D. This is a 4-input AOI. This is a 3-input AOI. Notice that I don't draw a line between my AND and OR, meaning that this is all one complex gate structure, A, B, C. All right, we are done with basic gate structures, and next will be the Boolean algebra and Boolean functions.